Hello students, today I will be discussed about the nuclear magnetic resonance spectroscopy, that means NMR. In our syllabus that is only one each included here. So first of all we have to know these three terms, what is called nuclear, then magnetic and then the resonance. So which one is called the resonance? What condition the resonance will be occur and which that will be explained first. We know that over the last 50 years NMR is the most strongest spectroscopy to evaluate the complete structure of a compound, mainly organic or protein, carbohydrate and others also. And although the amounts of the sample needed much more than for mass spectroscopy, but it is non-destructive. This occurs only in the radio frequency region, so the energy required for this is very small, and we can explain how the NMR phenomenon occurs. So first of all we have to know which nucleus are NMR active. Okay, so I have already written on the table here. You know that there is a nuclear spin or the nuclear spin quantum number that may be designated by I. That may be designated by I, and for different values of I, the nucleus may be NMR active or may not be NMR active. Now, for the organic chemist, it is very much fortunate that oxygen is not the NMR active. So why the NMR not active? That will be explained now. So there are three conditions. First, the mass number may be odd or atomic number may be odd or even. Atomic number may be odd or even. In that cases, the I values, that is nuclear spin or the spin quantum number of the nucleus is half, 3 by 2, etc. 5 by 2, etc. Then these compounds, these nucleus are NMR active. So the examples of this one, 1H and the 13C, 1940, etc. Now, if the mass number and the atomic number both are even, then the I will be the 0 here. That's the vector will be 0, and clearly they will be NMR inactive. So it is oxygen 16 oxygen and 12 carbon are NMR inactive. Now, if the mass number is even, it is another condition, and atomic number is odd, then its value of I is 1, 2, 3, etc. and still it will be NMR active. And such kind of nucleus, example of such kind of nucleus is deuterium, 14N, etc. So by this also, which nucleus are important for us? That is, we have in 13, 19 fluorine, etc. But we will be discussed here only the proton. Now, for the proton, that means for 1H1, the I is equals to half. So how many vector will be possible for this particular direction? This angular momentum vector for this one is angular momentum vector for the proton. How many? That is very important. The angular momentum vector for I equals to half is equals to what? That is 2I plus 1, that is the formula. So it will be 2 into half into 1, and we got the 2 here. So in presence of a strong magnetic field, what will be happened here? Okay, now we will move to the compound nitrogen. So the features of the NMR will be now discussed. Features of the 1H NMR will be now discussed. So there will be two energy states are possible for the nucleus containing I equals to half. So that will be this one. So in presence of this, there will be a such kind of rotation may be possible if one nucleus, that is one spin, may be rotated in this side, so that another can be rotated in this side, that means in this side. So by this way, one have the lower energy state and others will be in higher energy state. So these two spin will be in opposite direction to each other, and this magnetic moment term mu. So this magnetic moment is proportional to the corresponding spin. So its magnetic moment will be proportional to magnetic moment is proportional to mu. So mu is called the magnetic moment. It's proportional. Mu is proportional to its spin. So that means spin 6 may be anti-clockwise direction or it may be clockwise direction. Now, so in presence of the external magnetic field, what should be happening? So that is the second. So in presence of an external magnetic field, we call this one the external magnetic field will be represented by B0. This direction it will be represented by B0. So in presence of this external magnetic field, that is two spin states are exist. First one is what? That will be the plus up. That will be the plus up, and another spin state may be possible. That will be the minus up. So in these cases, that means in this direction, if let this one is plus up, so this direction it will be in the minus up direction. Okay, so this will be the direction. So clearly, there are two different energy states may be possible there. So in presence of the magnetic field, lower energy state is, so this is the B0, this is the actually B0, and this will be aligned with the external magnetic field. It will be aligned with the external magnetic field and it will oppose the external magnetic field. Now it will be may act as a teeny bar magnet also, so it's will be augmented. It will be plus here, that was the lower energy state. Which one is higher energy state? Its magnetic moment will decreases or experience the lesser amount of B0, that will be in separate in opposite direction. That's why there will be clearly two opposite energy will be there. So we may tell this is equals to H. So look at this nu here. That's the energy difference between these two. State is equals to H. Now the difference energy between these will be dependent on the amount of external magnetic field. Now, if we place this one is here, and if this one is energy goes there. So in absence of this, and this one is the B0, that is the value of B0 in B0. Now in case of, so clearly it will be increases here. So this is the actually difference. Delta E equals to mu into Bx divided by I. Here this amount of energy is called the Bx. So it will be the 0 here. So in absence of the external magnetic field, these two spin state was equal because they are in this type of, that is called the degenerate. These two will be degenerate. When you increase the B0 value, because this will is the B0 value, then this separation will be increases. So this amount will be increases with increase in the B0. That means it will be dependent on the amount of B0. Okay. So this one is energy difference for I, and mu is the magnetic moment of the nucleus. Here mu is the magnetic moment of the nucleus. One is in parallel, that will be lower in energy, another will be anti-parallel to the external magnetic field. This B0 is the external magnetic field. So external magnetic field will be opposed to each other. So by this way, so in presence of this external magnetic field, a energy separation will be occurs there. So it should be Bx. If the others, then it will be changes there. So this is one of the important relations of the NMR. So it needs a strong magnetic field because this value should be very much strong, and it is units is generally Tesla. That is unit of EMF is Tesla. Okay, unit of this capital T is called the Tesla here, and generally 1 to 20 Tesla are used here, modern NMR spectroscopy, but the NMR instrument is called with the megahertz. I come to later what is meant by the megahertz. So what should happen here? So in external magnetic field, there will be two phenomena as occurs in the nucleus. What are these phenomena? First phenomenon is, so two phenomena occurs in presence of this external magnetic field. What? Now first one is this one, that is it will takes the higher and lower energy field and it gives a characteristics motion. So with energy difference delta. So adopt two orientation first. The first phenomenon is adopt two orientation, and the second phenomenon adopt is two orientation with parallel and anti-parallel. So this one is called the parallel, this one is called parallel, and this one is called anti-parallel with respect to the external magnetic field, and we got the two energy difference just like this parallel and this one is anti-parallel, and a motion and a characteristics motion that is called the precisional motion. So this one has got a precisional motion is generated. Precisional motion is generated. So there will be some precisional frequency, and hence precisional frequency will be there. Okay, so that frequency will be nu. So that is this one. Okay, so this nu we call this as the precisional frequency. So clearly, with the increase of the B0, this precisional frequency will be increased. What is the precisional motion? It is a characteristics motion, just like a spinning top. We know that spinning top is have a motion around its axis and it's describe a path here. Okay, so this kind of motion is also called the precisional motion. So clearly it has an frequency, and that frequency is called the precisional frequency. Okay, so up to this we have discussed about what's happened in presence of an external magnetic field, that's a very strong magnetic field, to the nucleus. What's happened? An NMR active nucleus adopt two orientation first, that is one is parallel, another one is anti-parallel, plus half and minus half, and the energy difference occurs between them. Okay, and a characteristics motion is generated, that one is called the precisional motion, and hence there will be an precisional frequency. Generally this precisional frequency is equals to this one. Now, if we irradiate the sample with the frequency beam near about or exactly by the nu, then what should happen there? This will absorb that energy. That means it will be now gives an electromagnetic radiation. Electromagnetic radiation. What frequency? That will be radio frequency of radio frequency. I have already told before, the radio frequency energy is necessary for this one. That means this nu is corresponding to the radio frequency of the electromagnetic radiation. Now, if we irradiate, that means there is a NMR sample tube, NMR is there and it will be in the strong magnetic field. So such kind of precisional motion and other this orientation is occurs. Now we have supplied or irradiate this with the frequency near or exact with this frequency. Then what will be happen there? Now this frequency which will be supplied externally, that is external radio frequency, this energy will be absorbed by this and goes to here. That's why this is also absorption spectroscopy. Energy from the radio frequency taken up by this and goes to here. Yes or no? Of course. Then it will go to the higher energy state. After go to the higher energy state, it will relapse back. It will relaxes by the spin lattice or lattice spin relaxation or spin lattice relaxation and go back to the lower energy state. Yes or no? Go back to the lower energy state. Hence, the NMR processes can continue there. Now, when this situation arises, what situation? after getting the precessional motion, an absorption of the energy from this radio frequency beam of a particular nucleus, here the proton, absorb this energy and goes to the higher energy state and again relax back to here. This is actually called the resonance situation. Hence the term nuclear, because nucleus, NMR active nucleus must be involved there. Magnetic, there is a strong magnetic field that is given to you, and it is called resonance. And this resonance is with the external radio frequency and the corresponding precessional frequency generated here. Clearly the precessional frequency is corresponding to the external magnetic field. So if we take the external magnetic field 100 megahertz, 60 megahertz, that is Tesla, the corresponding instruments are 60 megahertz. Generally these are the radio frequency range, or it may be the 100 megahertz, or it may be the 300 megahertz, okay, and now 600 megahertz, etc. So due to the increase of the external magnetic field, then the corresponding precessional frequency will be increases. That means your radio frequency have to be higher. So this is the actually supplied radio frequency range, and instruments are named by the range of radio frequency. So we need higher amount of magnetic field, that is external magnetic field, for the 600 megahertz instrument, and we need lesser amount of B0, that is external magnetic field, for the 60 megahertz instrument. It means lower and it's need higher. So by this way, if we increases the external magnetic field, clearly its precessional frequency will be increases. As the precessional frequency will be increases, hence the radio frequency have to be increases to resonate with them. Yes or no? So by this way, we can explain which one is called the NMR. Okay. So this one is my part 1. Next, this one will be my part 1. I will come later in the next video. That is one called the chemical shift. Okay. In the next video, we will discuss about the chemical shift. That means chemical shift. Okay. So this will be in my next video. I will be discuss about the chemical shift. Which one is called chemical shift and how we can apply it to the external in the organic compound. So now, what information we can got from the NMR? What information we can got? How many kind of environment, that is different hydrogen environment or proton environment, are present in the compound that can be detected, and how many protons are present in each environment, okay, and which environment is adjacent to other. So such kind of informations are can be obtained from the single proton NMR spectrum. Okay, so the chemical shift will be discussed in the next video.